Hello friends and welcome to this video. We are with the adaptive filters to be the sixth chapter of the subject advanced digital signal processing. The various concepts we have covered in this particular chapter for the design of adaptive filters to be either FIR type finite impulse response and IIR type infinite impulse response. The categorization can also be into the non-recursive and the recursive types here. The previous video was the practice of problem number 1, whereupon the understanding we have used for the design of the Wiener filter, and there it was the use of steepest descent algorithm as well. Now here it is problem number 2 based on to the adaptive filters again. Especially here we are going to make the understanding that we have seen for the design of FIR filter using the steepest descent algorithm and also by the use of LMS algorithm, which is more popular and beneficial than that of the steepest descent algorithm here. So let us begin to see what is the exact problem statement and how do we find solution to this particular problem statement here. So let us start with it. So here we start with our topic, the topic titled problem 2. So as we have several of the methods for minimization of the mean square error, there it is one of the method called as the Newton's method. So the problem statement starts as Newton's method is an iterative algorithm that may be used to find the minimum of a nonlinear function. Applied to the minimization of the mean square error given as xi of n, that is equal to the expected value of it is square of e of n, where e of n is d of n minus the transpose of the weight vector w multiplied to the x of n here. The Newton's method is, the update equation is provided to us, that it is w suffix n plus 1 is equal to w suffix n minus 1 by 2 multiplied to the inverse of the autocorrelation matrix represented capital R suffix x further multiplied to the gradient of the mean square error xi of n here, or you can call it to be zeta, it is a Greek symbol. So here Rx, capital R suffix x, is the autocorrelation matrix of the input discrete time random process x of n. Now here introducing a step size parameter mu, the Newton's method become with a new form. The update equation is w suffix n plus 1 is equal to w suffix n minus 1 by 2 times mu into the inverse of capital Rx as it is into the gradient of the mean square error xi of n. The problem statement continues with comparing this to the steepest descent algorithm. We see that the step size mu is replaced with a matrix denoted mu into Rx inverse, which alerts the descent direction. Now exactly the questioning part is there, that is divided into the four. We have part A, B, C and D. In the part A, the question is for what values of mu is the Newton's method stable? That is, for what values of mu will w suffix n converge? So this is the question in part A. In the part B, the question is what is the optimum value of mu? That is, for what value of mu is the convergence the fastest? Next to that, in the part C, we have to make one more consideration, that suppose we form an LMS version of the Newton's method by replacing the gradient with a gradient estimate. The estimate is shown with cap over the del of xi of n, that is equal to del e square of n. We have to derive the coefficient update equation that results from using this gradient estimate and describe how it differs from the LMS algorithm. And there it is, part D. In the part D, we have to derive an expression that describes the time evolution of expected value of w suffix n using the LMS Newton algorithm derived in part C. So this is what a complete problem statement here. We get back to the details we have here. So here the problem statement starts with Newton's method. So here it is the Newton's method. So Newton's method as an iterative algorithm is utilized here for finding the minimum of the nonlinear function, and it has been applied for minimization of the mean square error that is given. We know that the mean square error is the expected value of the mod square of the error signal E of n. The error signal is difference of the desired signal and the output signal. So desired signal here it is denoted d of n. The output signal is denoted as the transpose of the weight matrix multiplied to the original input signal x of n that has both the components of the noise and the desired signal here. And for the method we have the information provided as the update equation. Here it is the one equation, and with the help of step size we have the another update equation here. So we have to compare this with the steepest descent algorithm that we have just now solved a problem based on, and also we have covered this topic as the third video from the same chapter. And we see that the step size is replaced with the matrix denoted. And now let us focus on to the part A. The part A is for what value of mu is the Newton's method stable, that is for what values of mu will Wn converge here. So let us answer this particular part here. So after part A, B, C and D here, we have to give a solution to part A. See, here we have to evaluate the gradient vector that we have been provided here. So the gradient of the minimum mean square error basically. So it is represented del into psi of n here. So it is equal to twice of the expected value of the error signal E of n multiplied to the gradient of E of n here. So this we can represent as minus 2 expected value of E of n into x of n. So this can also be regarded in terms of the cross correlation between the desired signal and the input signal x of n, and then the weight vectors and the autocorrelation matrix. So this we can write it as minus twice the cross correlation r suffix dx further added by 2 into rx into the weight vector w suffix n. So therefore, whatever the update equation we have for the method we have been provided, so that it is w suffix n plus 1 is equal to w suffix n minus 1 by 2 times mu into rx inverse multiplied to that it was gradient in the problem statement. In place of this gradient from the above representation, here we replace twice capital R suffix x into Wn minus twice R suffix dx here. So whatever we have determined to be the gradient of the mean square error, that we have substituted into the update equation, that is making the use of step size parameter denoted by mu here. So here we have w suffix n is equal to w suffix n plus 1 is equal to w suffix n minus mu times w suffix n added by mu times w. So this is equal to, we have 1 minus mu multiplied to w suffix n taken as the common added by mu into w. So therefore the Newton's algorithm will be stable for the range of step size mu greater than 0 but less than 2 here. So there it was the part A. The question it was, for what values of mu is the Newton's method stable, that is for what values of mu will Wn converge here. So we have utilized the update equation provided in the problem statement itself here, and by utilizing the same we have the answer that the stability we find for the step size greater than 0 but less than 2 here. Next to that, we have part B of the problem statement. The part B of the problem statement is, what is the optimum value of mu step size? That is, for what value of mu is the convergence the fastest? See, the convergence is fastest when we have the range as it is mu greater than 0 but less than 2. So there it will be mu is equal to 1 here. So here we can note that actually when mu is equal to 1, the Newton iteration converges to one step of the W here. So this is what the answer. The question it was, what is the optimum value of mu? For what values of mu is the convergence the fastest? The value of mu for the fastest convergence is 1 here. So this is solution to part B here. So after part B, we have part C. In the part C, there it is a consideration that we form LMS version of the Newton's method by replacement of the gradient with the gradient estimate. The gradient estimate is also provided to us. We have to derive the coefficient update equation that results from using the gradient estimate and describe how it differs from the LMS algorithm here. So for solution to be a part C here, the gradient approximation, here we use the gradient. It is made with the notation of del along with the square of the error signal E of n. So del E square of n, that is equal to minus 2 multiplied by E of n into x of n. This is the gradient approximation. So therefore, as we have to make a consideration of forming LMS version of the Newton's method, the LMS type algorithm can be with the help of the update equation denoted by W suffix n plus 1, that is equal to W suffix n added by the step size mu into the error signal E of n into the inverse of the autocorrelation matrix capital R suffix x into the input or the relative signal x of n here. So let us have comparison of this update equation to the LMS algorithm. So thereupon the observation is that the step direction is changed from x of n to the inverse of the autocorrelation matrix multiplied to x of n here. So the question that it was, derive the coefficient update equation that results from using the gradient estimate. So here we have the update equation denoted W suffix n plus 1 added equal to W suffix n added by mu into E of n into inverse of the autocorrelation matrix capital R suffix x into x of n here. And the accompanied question was, describe how it differs from the LMS algorithm. The answer is, the step direction has been changed from x of n to inverse of autocorrelation matrix R multiplied to x of n here. Next to that, we have part D. In the part D, we have to derive the expression that describes the time evaluation of expected value of W of n using the LMS Newton algorithm derived into the part C here. So for answering this particular question from part C, we take the update equation that is suitable for the part D derivation, that it is W suffix n plus 1 is equal to W suffix n added by mu into the inverse of the autocorrelation matrix capital R suffix x multiplied by x of n into d of n minus mu times inverse of the autocorrelation matrix again capital R suffix x into x of n multiplied to the transpose of x of n into the weight factor that is represented W suffix n. Either you call weight factor or the weight vector here. So instead of making the use of error signal, the difference, which is basically the error, here we have utilized for the desired signal and the output signal here. That is why we have the three terms onto the right hand side here. So let us make one assumption here that x of n is totally uncorrelated with the filter tab weight vector denoted by W suffix n. So for the uncorrelation between x of n and W suffix n, we have the expected value of w suffix n plus 1, that is equal to the expected value of w suffix n added by mu into the inverse of capital Rx into the cross correlation R suffix dx minus mu into inverse of capital Rx into capital Rx into the expected value of w suffix n here. So finally it becomes the form the expected value of w suffix n plus 1 equal to 1 minus mu multiplied to the expected value of w suffix n further added by mu multiplied by w. So as it was the question to derive the expression describing the time evaluation of expected value of w suffix n using the LMS Newton algorithm from the previous part, here we have obtained the expression that you can outline, and this is the solution to part D of the problem statement here. So this was our problem number 2 based on to the understanding of the steepest descent algorithm and further the LMS algorithm and the new methodology according to the Newton for minimization of the mean square error here. So after this, by the next lecture we shall have one more problem to practice based on to the various topics we have covered for the design of the adaptive type of the filters to meet the requirement of the various signal processing applications. Thank you.